What I am going to show you today is the mathematical reason that the objects in an odd-numbered cascade juggling pattern tend to pair up at certain instances in time, as you can see in these pictures. This effect generally goes unnoticed by the majority of jugglers and audiences, but it is very interesting to derive and has some relevance in the real juggling world. For example, it can be used to analyze how solid one's juggling pattern is if a video is taken. It can also describe a certain visual effect caused by juggling 5 clubs in particular. This pairing up effect is present in even-numbered juggling also, with slight variations. The mathematics shown in this tutorial will only consider the odd-numbered case, though this tutorial can be used as a guideline for considering the even-numbered case. Here we have the flight path of objects in a cascade pattern. We are trying to prove that the objects will indeed pair up like this. The direction that these objects are going in is such that the inside paths are always going up and the outside paths are always going down. There are a few pieces of information that we must label in order to begin. Firstly, we have the height of the juggling balls above the juggler's hands, which is the thin horizontal line drawn towards the bottom of the diagram. Let the maximum height be capital H. Also, we are proving this effect for any n number of objects where n is odd. Therefore, the top of this diagram can extend indefinitely. Now, in order to find the period of the juggling pattern, or total time that an object is in the air, we can draw a site swap diagram. Site swap notation ignores the time that a ball is being held, which makes things relatively simple. In this diagram, a ball is thrown, and capital T units of time later, or n beats later, the ball is caught. In a complete and properly drawn site swap diagram, unlike the one shown here, it is easy to see the pairing up effect by looking at the intersection of the flight paths. However, we are going to prove why all these balls must line up at the same time. We are going to label each ball in this diagram according to the order that it was thrown. The first ball to be caught was obviously the first ball to be thrown, so we label this ball 1. We label the second ball that is about to be caught 2, the third ball 3, the fourth ball 4. And working backwards, the final ball to be thrown, which is still being held in the juggler's hand right now, is the nth ball. The ball that was thrown right before the nth ball is about to be thrown is the n-1th ball, and so on. Let's say that the first ball was thrown at time t equals 0. We know that in this cascade pattern, the time between each consecutive throw is constant. This interval of time between throws can be given by the total period of the pattern divided by how many objects there are, or capital T over n. Therefore, if the first ball was thrown at time 0, the second ball will be thrown at time capital T over n. The third ball will have been thrown at time 2 capital T over n. And following this pattern, the n-1th ball will have been thrown at time n-2 capital T over n, and the nth ball will have been thrown at n-1 capital T over n. The equation shown in red is the basic equation for the height of a projectile under constant acceleration as a function of time. V represents the initial velocity that the object was thrown with, and the A represents the acceleration that the object is experiencing, which in this case is gravity. Now, since velocity is a variable, let us solve it in terms of capital T. If we say that the height of the hands where the ball is thrown is a height of 0, then we know that after big T units of time later, that object will be at 0 height again. Now, we solve this simple equation and find out that velocity is equal to gravity times big T all over 2. Let's take this result and substitute it back into the original equation for the height of the object. And we can simplify this a little bit by taking out gt over 2. Now, looking at the original diagram in the top left there, we see that the first ball and the n-1th ball line up. So, if the first ball was thrown at time 0 and the n-1th ball was thrown at a certain time after this, we must find at what point in time the two heights are equal. Let's say that the amount of time representing how long the first ball has been in the air is lowercase t. Therefore, the amount of time that the n-1th ball has been in the air is this measure of time lowercase t minus n-2 big T all over n, which is shown by the orange equations in the top left. Now, we plug in the time that the first ball has been in the air, lowercase t, and the time that represents how long the n-1th ball has been in the air, into the equation for height as a function of time. Then, we set these two expressions for height equal to each other. We immediately see that g over 2 cancels on both sides. Now, we are going to simplify this expression circled in red. We are left with 2 times capital T times n-1 all over n minus little t, and substitute this back into the equation. We multiply out everything on both sides of this equation, and we are left with what is shown. Lowercase t squared cancels out on both sides. Then we move all the terms that have a lowercase t onto one side of the equation. The workspace has been cleared and this equation has been rewritten on top. We simplify the side of the equation that has all of the lowercase t's. Big T times little t times n cancels, and the rest of the expressions combine. We factor out a 2 big T little t. We get the negative sign out of the right side of the equation, and a lot cancels out, leaving us with the result that the time after the first ball has been thrown, where this first ball and the n-1th ball go to the same height, is at time big T times n-1 all over n. What may not have been so obvious from this result to someone who does not study site swap notation too much is that the time that the first and the n-1th ball cross the same height is the same time that the nth ball is being thrown. Now that we have shown, written here in gray, the time after the first ball has been thrown that this first ball and the n-1th object will be at the same height, we must show that every other pair of juggling objects will be at the same height as its partner at the same time. In other words, the height of one juggling object is equal to the height of its corresponding juggling object, which was thrown at a certain time later. Some pairs of objects that will line up are the second object and the n-2th object, and the third object and the n-3rd object, and so on. The time differences corresponding to when a certain ball is thrown and when the first ball is thrown are shown here, as you can see from the orange equations in the top left. Through some careful observation, you can see that there is a pattern for the time differences that correspond to a pair. Namely, the time corresponding to the earlier ball is the initial time minus x capital T over n, and the time of the later ball corresponds to t minus n minus x plus 2 big T all over n. X is simply an integer that corresponds to a pair of objects. We previously found the time that any pair should cross heights, as written in gray. We plug this value of time into the arbitrary lowercase t in the two expressions that we just deduced, and simplify. Any objects that have been in the air for times corresponding to those written in red boxes should be at the same height. In order to prove this, we plug those two times into the equation for height as a function of time written in red on top. We do quite a bit of simplifying, and thus prove that all juggling objects will line up simultaneously in an odd-numbered juggling pattern, with one ball being held in the juggler's hand.